NENOMATICA, where mathematics meets YouTube excellence. The first law of power. Welcome to our math lesson on exponents. Today, we're going to learn about the product of powers rule, which is a fundamental property for working with exponents. Let's start with the rule itself. The product of powers rule states that when multiplying powers with the same base, we add the exponents. This can be written formally as, for all values of a in the real numbers and m and n in the integers, a raised to the power m times a raised to the power n equals a raised to the power m plus n. Let's break down what this rule means with a simple example. Suppose we have 2 squared times 2 cubed. Using the product of powers rule, we can add the exponents. 2 plus 3 equals 5. So 2 squared times 2 cubed equals 2 to the 5th power. Now, let's prove why this rule works. We'll start with the expression a to the power m times a to the power n. Let's expand what these exponents actually mean. A to the power m means a multiplied by itself m times. Similarly, a to the power n means a multiplied by itself n times. When we multiply these expressions, we're essentially combining all these a's together. So we have a multiplied by itself m plus n times. And by the definition of exponents, this is equal to a raised to the power of m plus n, which completes our proof. Let's understand this with a visual representation. Imagine we have 2 raised to the power 3, which means 2 multiplied by itself 3 times. So that's 2 times 2 times 2, which equals 8. And we also have 2 raised to the power 2, which is 2 times 2, which equals 4. So when we multiply 2 to the power 3 times 2 to the power 2, we're multiplying 8 times 4, which equals 32. And 32 is exactly 2 raised to the power 5, or 2 raised to the power 3 plus 2. Let's look at one more example to make sure we understand. Consider 3 raised to the power 4 times 3 raised to the power 2. Applying the product of powers rule, we add the exponents. 4 plus 2 equals 6. So 3 raised to the power 4 times 3 raised to the power 2 equals 3 raised to the power 6. Let's calculate this another way to verify. 3 to the power 4 equals 81, and 3 to the power 2 equals 9. Multiplying these together, 81 times 9 equals 729. And indeed, 3 raised to the power 6 equals 729. It's important to note what this rule does not say. The product of powers rule only applies when the bases are the same. For example, 2 to the power 3 times 3 to the power 2 cannot be simplified using this rule because the bases 2 and 3 are different. Also, be careful not to confuse the product of powers with the sum of powers. A to the power m plus a to the power n is not equal to a to the power m plus n. These are completely different operations. Let's summarize what we've learned. The product of powers rule states that when multiplying powers with the same base, we add the exponents. This can be expressed as a to the power m times a to the power n equals a to the power m plus n. This rule helps simplify expressions with powers and is one of the fundamental exponent rules in algebra. Let's start with our first example. We have 2 to the power of 6 times 2 to the power of 7. To solve this, we'll use the product rule of exponents. When we have the same base with different exponents being multiplied, we keep the base and add the exponents. So, 2 to the power of 6 times 2 to the power of 7 equals 2 to the power of 6 plus 7, which gives us 2 to the power of 13. Let's move to our next example. We have 3 to the power of 2 times 3 to the power of 4 times 3 to the power of 5. Again, we'll apply the product rule of exponents. Since all terms have the same base, 3, we add all the exponents. So, we have 3 to the power of 2 plus 4 plus 5, which equals 3 to the power of 11. Let's look at our third example. We have 9 times 3 to the power of 4. To solve this, we first need to rewrite 9 as a power of 3. Since 9 equals 3 squared, we can rewrite our expression as 3 squared times 3 to the power of 4. Now we can apply our product rule of exponents again. We get 3 to the power of 2 plus 4, which equals 3 to the power of 6. Now, let's look at a more complex example. We have 2 to the power of 6 times 2 to the power of 3, all raised to the power of 4. First, we need to apply the power of a power rule. when we have a power raised to another power, we multiply the exponents. So 2 to the power of 3, all raised to the power of 4, equals 2 to the power of 3 times 4, which is 2 to the power of 12. Alternatively, we can expand this as shown in the image, 2 to the power of 3 multiplied 4 times. Now we have 2 to the power of 6 times 2 to the power of 12. And using the product rule, we add the exponents. 6 plus 12 equals 18. So our answer is 2 to the power of 18. Let's start with our first example. We have 1/5 times 1/5 times 1/5 times 1/5. When we multiply the same base multiple times, we can rewrite each term with an exponent of 1, as shown here. According to the product rule, for exponents, when we multiply powers with the same base, we add the exponents. So we get 1/5 raised to the power of 1 plus 1 plus 1 plus 1, which equals 1/5 to the power of 4. Let's look at our second example. We have the square root of 3 multiplied by itself 5 times. We can rewrite this as the square root of 3 raised to the power of 1 5 times. Using the same product rule, we add all the exponents together. So we get the square root of 3 raised to the power of 1 plus 1 plus 1 plus 1 plus 1, which equals the square root of 3 to the power of 5. For our third example, we have a over 2 multiplied by itself 5 times. Following our pattern, we can rewrite this as a over 2 with an exponent of 1 5 times. Again, applying the product rule for exponents, we add all 5 exponents to get a over 2 to the power of 1 plus 1 plus 1 plus 1 plus 1, which equals a over 2 to the power of 5. In our fourth example, we have the binomial expression a plus b multiplied by itself 3 times. Just like before, we first rewrite each factor with an exponent of 1. Using the product rule, once more, we add the exponents to get a plus b to the power of 1 plus 1 plus 1, which gives us a plus b to the power of 3. Here's our fifth example with powers of 10. We have 10 times, 100 times, 1,000 times 10,000. First, we rewrite each number in its exponential form. Now, we can apply the product rule. We add all the exponents, 1 plus 2 plus 3 plus 4, which equals 10. So our answer is 10 to the power of 10. Our final example involves 2.5 to the power of 7 times 5 halves to the power of 3. First, notice that 2.5 is the same as 5 halves. So we have the same base in both terms. Since we have the same base, we can add the exponents. 7 plus 3 equals 10. So our final answer is 5 halves to the power of 10. Let's review some important tips and rules about exponents. Remember, when multiplying expressions with the same base, add the exponents. And remember that this rule only works for multiplication, not addition. Here are 2 more important rules to remember. If 2 expressions with the same base are equal, then their exponents must be equal. And when you raise a power to another power, you multiply the exponents. Let's summarize what we've learned today. We explored the product rule for exponents, which says that when we multiply the same base, we add the exponents. We saw this rule applied in various examples, from simple fractions to binomials and powers of 10. These rules form the foundation for more advanced topics in algebra and calculus. Today, we'll solve a problem to find a relation between 2 variables that is independent of a third variable. Let's look at our problem. We are given that a equals x raised to the power of 1 over x minus 1, and b equals x raised to the power of x over x minus 1. We need to find a relation between a and b that does not involve x. Let's start by working with the expression for b. We'll rewrite the exponent of b by adding and subtracting 1 in the numerator. We can rewrite x in the numerator as x minus 1 plus 1. Using the laws of exponents, we can split this into a product of powers. The first exponent simplifies to 1 because x minus 1 over x minus 1 equals 1. And notice that the second term is exactly our definition of a. So we have b equals x times a. From our equation, b equals x times. We can solve for x in terms of a and b by dividing both sides by a. This gives us x equals b over a. Now, let's go back to our original definition of a. We have it equals x raised to the power of 1 over x minus 1. We'll substitute our expression for x into this formula. Actually, instead of substituting into the formula for a, Let's use our formula for b, which is b equals x to the power of x over x minus 1. Since we know x equals b over a, we can substitute this into the definition of b. Since it equals x to the power of 1 over x minus 1, we can also write b in terms of a. Let's look at what happens. Now, let's substitute x equals b over a into the formula for b. We have b equals x to the power of x over x minus 1. But actually, there's an easier approach. Let's use the fact that b equals x times a. We can express b in terms of a and x. We also know that it equals x to the power of 1 over x minus 1. Let's solve for x in terms of using this relationship. Now, we can substitute this expression for x into our equation b equals x times a. Using the laws of exponents, we can simplify this to b equals a to the power of x. Finally, we can substitute our earlier result that x equals b over a. Therefore, we have found our relation between a and b that is independent of x. The relation is b equals a to the power of b over a. This expression contains only a and b, with no x, which was our goal. In this problem, we used algebraic manipulation and the properties of exponents to eliminate the variable x from our equations. Thank you for watching. Don't forget to like, subscribe, and hit the bell icon for more math lessons. NENOMATICA, where mathematics meets YouTube excellence.